Welcome to this 33rd Melo lecture. My name is Erik Offerman. I work at the Department of Material Science and Engineering of Delft University of Technology. Now let me share my screen and start my presentation about the topic of some attempts to better understand the phenomenon of solid-state nucleation in steel. So before I start, let me say that I had the pleasure of working on this topic over an extended period of time with a lot of colleagues from Delft and Ghent University and also from DTU in Denmark. And I've also had structural funding from the Dutch Organization for Scientific Research, the Materials Innovation Institute in the Netherlands, from Tata Steel, and the Science and Technology Facilities Council in the UK that provided neutron beam time, and the European Synchrotron Radiation Facility that provided synchrotron radiation beam time. So why is solid-state nucleation scientifically relevant? Well, all solid-state phase transformations start with a nucleation phase. And here you can see two FCC grains with VCC nuclei having special crystallographic orientation relations with their parent grains, as indicated here by the asterisks. Nucleation also takes place during recrystallization of a deformed microstructure. So you see here a deformed microstructure, and here you see a nucleus of a recrystallized grain. Precipitation reactions, here you can see nanometer-sized vanadium carbide precipitates that formed during interface precipitation. They also start to form by the nucleation process. So understanding nucleation in the solid state is important for solid state phase transformations, recrystallization, and precipitation. Now, from an engineering perspective, solid state nucleation is important for through process modeling of steel, as you see in this case. And this is work done by Jesus Calan Lopez. And yeah, crystallographic aspects are also important for the development of the texture. Now, how to calculate the nucleation rate? This is a nucleation rate equation that is quite often used, where you see the density of potential nucleation sites, a frequency factor, which describes how frequent atoms are added to a subcritical nucleus, the Zeldovich non-equilibrium factor, and we have here the activation energy for nucleation, which is a very important parameter, and the incubation time for nucleation, which basically describes the characteristic timescale on which the transition from the transient nucleation rate to steady state happens. So it takes some time before the steady state nucleation rate is reached. Now there's also a summation, because nucleation at grain corners may not be the same as nucleation at grain edges or triple junctions. So to get the total nucleation rate, you need to add up all the different contributions of the nucleation rate. Now, how to calculate the activation energy for solid-state nucleation, which nucleus shape to choose, which strain energy to take, which interface energy values to select, and which composition of the nucleus to assume. So one way of writing the activation energy for nucleation is in this form, where you see geometrical factors which are related to the area of certain interfaces of the nucleus and the associated interface energy. And there's a summation here, because a nucleus might be described by different interfaces, different areas, as opposed to a spherical nucleus that's just one area. There are here a volume factor, so a shape factor. There's the strain energy, and there's here the driving force for the nucleation. Now, I find it convenient to group the terms that are related to the shape of the nucleus and the interface energies in a psi parameter. So that's basically this part of the equation. Now, two classical examples of nucleus geometries are the Clement-Fisher model, already from 1955, which assumes that nucleation takes place at grain corners, and you see here spherical caps in the four different parts of the four grains that form the grain corner. When you calculate the psi factor for this kind of nucleus, you come to values of 7 times 10 to the minus 3, joule to the power 3, and meter to the power 6. And in this model, they assume that all the interfaces are incoherent, and the nucleation here in this case is at grain corners, but they've nicely shown that if you assume incoherent interfaces, that nucleation at grain corners has a lower barrier for nucleation than nucleation at triple junctions, which in turn has a lower barrier for nucleation than nucleation at the edges. Then a model was used by Lange, Enomoto, and Aronson, and the so-called pillbox model, which described their experimental observations of ferrite nucleation rates in austenite well. And this model has the shape of a pillbox, and it contains coherent interfaces here at the bottom and here at the top, indicated by the C. And the edge of the pillbox is semi-coherent. And the idea here is that the coherent interfaces are low of energy. In other words, the psi value can be relatively low because there is a more close balance between the energy that it costs to form the new interfaces and the energy that is released to the system due to the removal of the former austenite grain boundary here. And if that is getting into close balance, energy needed for formation of interfaces, and that is energy that is released to the system because of removal of this interface, you can end up with relatively low psi values. Okay, then we did, during the time that I did my PhD, a synchrotron radiation experiment. The third generation synchrotrons just became active and had this newly developed technique of 3D XRD microscopy, by which you can measure in situ the nucleation rate. So we did that during ferrite formation from austenite in a carbon steel during continuous cooling. And what we observed was the nucleation rate as measured did not match with the classical nucleation theory if you fill in the typical values of the pillbox model with the typical interface energy values. So if we were to match the classical nucleation theory with our experiment, we needed to reduce the psi value by approximately 2 orders of magnitude, which also means that the activation energy for nucleation is 2 orders of magnitude smaller because they're directly proportional. Now we repeated this experiment on a steel with 0.35 and 0.45 carbon, and this was one with 22% carbon. And in all cases, we find a very low psi value, meaning that the activation energy for nucleation is lower. Now, just a little background about the measurements. What we actually measure is the growth of individual grains and not per se the nucleation event itself. And so with these synchrotron sources, we can record diffraction patterns, and in a very short period of time, a fraction of a second, we can record these patterns at elevated temperatures. So this is during the austenite to ferrite phase transformation, where you see here diffraction rings from the austenite, and here you see diffraction rings from the ferrite, and these points are diffraction spots coming from individual grains in your steel. So by probing how the intensity of an individual spot evolves, we're basically probing how the volume of the ferrite grain increases. And this is the volume of the ferrite grain, one individual ferrite grain as a function of temperature. And here is the growth curve of another ferrite grain. And here are other examples of ferrite grain growth curves during the phase transformation. Now, the resolution here is 2-3 microns. So when the particle has a radius of 2-3 microns, we start to observe it with this technique, which is, of course, after the nucleation event has taken place. So what do we do to determine the moment at which this grain nucleated? We make the assumption that this linear part of the growth curve can be extrapolated to the moment of nucleation, and the same here, which is an assumption because we don't know exactly what happens below these 2 microns. At the nanometer scale, the growth behavior could be different, but from these curves, it seems to be a reasonable way of determining the moment of nucleation of these grains. Okay, then there was a statement by Aronson that our results appear doubtful. And yeah, I remember I was impressed by how well they understood how we performed these experiments without themselves doing the experiment. And yeah, the reply we had to this statement basically was that we think that there is maybe another geometry of the critical nucleus that could result in a lower psi value as we observed from our measurements. So in fact, that stimulated me to the discussion to look more into it. So if you look at this psi value, then you see here the shape parameters and you see here the interface energies. Yeah, and if there is a good balance between the energy that is needed for the formation of low energy interfaces and energy that is released to the system, possibly higher energy interfaces, then these psi values can be relatively low. So theoretically, it might be possible that there is an energetically more favorable nucleus shape and interface energy than the pillbox. And then the question is, what is the role of crystallography? Because in order to form these low interface energies, the prerequisite is that you need to have special crystallographic orientation relations between the austenite and the ferrite. So then the PhD thesis of Escalante started, and we looked at a special alloy, an iron 20 chromium 12 nickel alloy, just these 3 elements, and we looked at the formation of austenite, the formation of ferrite in austenite. And this was work together with Ruben Petrov and Leo Kestens, who have a lot of expertise in crystallography and EBSD, from which I learned a lot at least at that time. And yeah, what we basically measured was this austenite microstructure, and it was completely austenitic at room temperature. And when we heated it up to 1400 degrees, you see these BCC nuclei here in black that started to appear. And by cooling down this microstructure, you can freeze in the structure that you have at 1400 degrees. So this allowed us to experimentally observe the austenite grains and the ferrite grains that you see here. This was 20 minutes annealing at 1400 degrees. This is 100 seconds. So seconds, 20 seconds, 100 seconds annealing at 1400. And in this measurement, we had a slight deformation of the sample of 0.2%. And this one was also annealed for 100 seconds at 1400 degrees. And you already see that due to the deformation, we have many more nuclei forming. Now, the orientation relationships that we looked into are given here. So Gurdjieff-Sachs, Nishiyama, Wasserman, the pitch, Greninger, Triano, the inverse grain Triano, all represented here. So these special crystallographic orientation relationships we've studied in detail. And here you see a number of examples of the nuclei or the grains that passed already the nucleation stage that we observed in our sample. So there are many more nuclei, but these are just a couple of examples. And the thick black line here means that there is a special crystallographic orientation relation between the FCC parent grain and the PCC product grain. And it has a special crystallographic orientation with both FCC grains on both sides. So that means that the two FCC grains should also have a special crystallographic orientation relation to each other. And this is indeed observed as a twin boundary. So you could say that this nucleus would correspond to the pillbox model. So we did find support for the pillbox model in these experimental observations. We also found nuclei that have only with one austenite grain a special crystallographic orientation and not with the other. So that would correspond to the pillbox spherical cap model. We have nuclei that form in the bulk of the material, in the interior of the grain, with an orientation relation all around. And we have nuclei again with only on one side the crystallographic orientation relation looks like this one, but then slightly different. So yeah, it makes sense that special crystallographic orientations are present between the product and parent grains, because that could lead to coherent interfaces that are low in energy and that would reduce the activation energy for nucleation. Now, Hiskeland here made an analysis of the number of ferrite grains per unit area of unreacted austenite grain phase. And you can see here the grain boundary length, the austenite grain boundary length that she subdivided into low angle grain boundaries, high angle boundaries, and twin boundaries. And here you see the number of ferrite grains per unit unreacted for the three different conditions: annealing, 20 seconds, 100 seconds, and deformation plus annealing for 100 seconds. Now, if you analyze all those results, you can make this tree-like structure where here are the grains that do have an orientation relation with at least one parent grain. So for the sample annealed at 1400 degrees for 20 seconds, almost 90% of the grains did have an orientation relationship with at least one neighbor. For the one annealed at 100 seconds, it was a bit lower, and for the one annealed plus some deformation, it was also a little bit lower. And then there were also grains that did not have an orientation relationship at all with the parent. And then this was subdivided into intergranular nucleation, nucleation at phases, at triple junctions. And at phases, we can distinguish again between nucleation at low angle boundaries and at high angle boundaries. And high angle boundaries can be subdivided again in twins, CSL boundaries, and random high angle boundaries. And this can then again be subdivided into nuclei which had orientation relations all over and on one side. Now, if you analyze all of this, you can come to the following conclusions, namely that almost 90% of the ferrite grains have a specific crystallographic orientation relation with at least one austenite grain, or at least along part of the phase boundary. And that implies that specific orientation relationships play an important role during the nucleation of ferrite. Ferrite nucleation is observed at triple junctions, grain edges or corners. We couldn't tell from this experiment because it was 2D observations. At the grain phases and intergranularly, and approximately half of the nuclei appear at grain phases. A slight deformation leads to a threefold increase in the number of nuclei, and the observations could be related to nucleus shapes that were previously defined by Clement Fischer, the coherent pillbox model, and the pillbox spherical cap model. Okay, so now we know that special crystallographic orientation relations play an important role in the nucleation, but we have not in one experiment correlated the crystallography to the activation energy for nucleation. And there could be some intervening variables that play a role, and there is, I can already tell, the strain energy also plays an important role during the nucleation. So here we observed austenite formation from ferrite in carbon steel, because we also want to know in carbon steel how the nucleation mechanism works, not only in the highly alloyed stainless steel-like compositions. So this is the work of Hemant Sharma during his PhD studies. And yeah, the starting point for his studies was the work of Landheer, where you see that special crystallographic orientation relations are very important because they can reduce the activation energy for nucleation. But yeah, the strain energy may also play a role. And in this case, coherent interfaces might lead to a higher strain energy, which would increase the activation energy for nucleation. And that's shown here, work by Lee et al., which shows that if you have a coherent precipitate, the strain energy is higher than when you have an incoherent precipitate, and it also depends on the geometry of the nucleus. So this is an ellipsoidal shape, and here the A and B axis are the same, and the C and B axis can be different, and that's here indicated by the parameter B and varied here along the x-axis. And when beta is equal to 1, we have a sphere, and otherwise we have this ellipsoidal geometry. And again, when we assume incoherent interfaces, the strain energy turns out to be lower than in the case of a coherent precipitate. So yeah, on the one hand, coherent interfaces may help in reducing the barrier for nucleation. On the other hand, higher strain energy may actually increase the activation energy for nucleation. So we asked ourselves the question, how does the activation energy for solid state nucleation depend on the number of special crystallographic orientation relationships between the nucleus and the surrounding matrix grains? So to schematically indicate the idea that we had before the experiment was that you might have an austenite nucleus with 4 ferrite grains nucleating here in the grain corner of these 4 ferrite grains, and with how many ferrite grains does this austenite nucleus have a special crystallographic orientation relation? And yeah, if it has more special crystallographic orientation relations, would then the activation energy for nucleation be lower or not? So we did a special experiment for this. This was also a singleton radiation experiment where we heated the steel very slowly. This was the composition. So we went up in small steps of 2 degrees, where we intermediately had let the system stabilize. So we go through the 2-phase region of austenite and ferrite, and in every step more austenite forms, but we stabilize the system and all the austenite forms at that temperature, and then we do a 3D measurement where we can probe the 3D microstructure of the steel at elevated temperature. So this is a schematic of the setup. We have a synchrotron beam, high energy X-rays entering a furnace. We have here very small our sample, and we have here the X-ray diffraction detector that records the diffraction patterns. So this is the furnace we specially made for this experiment, where we have here the steel sample, and from the back, synchrotron beam enters the furnace, and there's open space here behind, and then it interacts with the steel sample, and then towards us there is a X-ray detector. And here you see schematic. So the beam enters the furnace. There's our sample placed in a ceramic tube with heating coils, and this sample can freely expand upon temperature changes, just to avoid the introduction of deformation, as we've seen in the work of Landheer, that small amounts of deformation can already significantly increase the nucleus density. All right, and yeah, this is then the kind of information we obtain from the experiment. So in the volume that we probe, we see here all the ferrite grains, and yeah, what do all these spheres mean? Yeah, so the spheres are individual ferrite grains in the bulk of the steel sample, and we know of every ferrite grain exactly where in the sample it is located. So the center of mass is accurately known. We know the volume of the ferrite grains, but we do not know the geometry. So the geometry is not known, and hence we indicated it here by spheres. And the spheres are a little bit smaller than what they should be, but that's for representation purposes. Otherwise, you could not see the entire sample. And the color coding is related to the crystallography of all the ferrite grains. Now at 830 degrees, the steel sample is completely ferritic, and then we went 2 degrees higher and another 2 degrees higher. And here you see the same ferrite, but at the same time here at the bottom, we see austenite grains have formed. And when we increase the temperature, more austenite grains have formed, and we start to see a reduction in the number of ferrite grains. And this process continues as we step by step increase the temperature. Ferrite reduces and more austenite grains appear until at 848 degrees centigrade, all the sample is transformed to austenite. Now, with the crystallographic orientation information, we also can probe what are the relationships between the ferrite and the austenite grains. And you see here the ideal KS orientation relation, and here the ideal Nishiyama-Wassermann orientation. And this is the deviation angle in the plane. And so if we just moving forward a little bit quickly, in the KS orientation relation, and also for the Nishiyama-Wassermann, the planes need to be parallel, and these directions need to be parallel, so for KS and for Nishiyama-Wassermann. And that is what you see basically here. And all these dots show the correspondence between the ferrite and the neighboring austenite. And a lot of points show a near KS orientation relation, but also some deviations of a few degrees in the plane direction from that. And also in the a deviation in the angular direction. So there is not a perfect KS or Nishiyama-Wassermann orientation relation, but close to it in many cases. So if we do a more statistical analysis, we have here the ideal KS and the ideal Nishiyama-Wassermann, and we see that the majority lies close to KS, but there is also substantial deviation of it. And yeah, same here for Nishiyama-Wassermann. There's a large portion following it exactly, but also deviations from it. And the same is true for the misalignment of the planes. So it turns out that 74% of the orientations are of the KS type. And in our analysis, we said, okay, there is an orientation relation. If the maximum deviation is less 3 degrees in terms of the planes, and in terms of the angles between the directions, 12 degrees. Okay, then we looked at how many austenite grains have no orientation relationship with any of their neighbors. So that was a fairly small amount. Most of the austenite grains had at least had a special crystallographic orientation relation with only one. I should say it like that, only one. Fewer had with 2, with 3, and very special, I would say, also with 4 neighboring grains. So an austenite grain had 4 special crystallographic orientations with 4 neighbors. And to be complete, we did not observe any grains that had a special orientation relation with 5 grains. Now here you see the number of nuclei as a function of temperature. And this is the overall formation of new nuclei as a function of temperature. And the special thing about this graph is that we can now subdivide it into the different components that it consists of, namely austenite grains without any special orientation relations with neighboring ferrite, with only 1 ferrite, with 2 ferrite, with 3, and with 4 ferrite grains. So we can now also do a fit to the classical nucleation theory, except for the one with 0 special orientation relations, because we had too few data points. But here we have the austenite nucleation rate as a function of temperature. This is what we've measured, and in red there's a fit to the classical nucleation theory. So the case where there is 1 special orientation relation with 1 neighbor. So what kind of fit did we do? We had here the nucleation rate equation, activation energy for nucleation. We filled this in over there and ended up with this equation for the beta. We used this term, and we look at the number of nuclei per unit transformed matrix. So we also have the ferrite fraction in here, which depends on temperature. We have the density of potential nucleation sites, and we have the driving force for nucleation, which depends on temperature and can be obtained from thermo-mechanical calculations. And we have the strain energy, which we take from the paper of Lee. And we have one more prefactor alpha here in front. Now, the density of potential nucleation sites changes as a function of temperature, because when you have more nuclei forming, the density of potential nucleation sites should decrease because they're fewer because of the formation of nuclei. And we measure the number of nuclei, and we assume that then this is the way the density of potential nucleation sites reduces as a function of temperature. So it could be maybe there could be a prefactor here in front, because we don't know which potential nucleation sites have not been activated. So the number of potential nucleation sites could be higher, but we assume that this shape is like this when we plot it as a function of temperature. Now, the austenite fraction we can obtain from integration of the diffraction rings, so that's simultaneously obtained from the measurements. And the driving force we calculate by means of thermocalc. And under para-equilibrium, we expect the transformation to start at this temperature. And experimentally, we observe that the transformation starts at this temperature. And the interesting thing is that at this temperature, the driving force is 11 megajoule per cubic meter, and expressed here in megajoule per cubic meter because we want to compare it to the strain energy, which from Lee et al. Is of the order of 10 megajoule per cubic meter. So here, this moment is actually the moment where the driving force is just above the strain energy, and that is indeed a criterion for the start of the nucleation, and you need to have at least the driving force to overcome the strain energy. Now, we did the fits to the classical nucleation theory in case there were 2 special orientation relations between the austenite nucleus and the ferrite grains. The same for 3 and for 4 orientation relations. And when you summarize it here, you find for this psi parameter as a function of the number of special orientation relations, that the more special orientation relations there are, the lower this psi value is. And this psi value directly translates into an activation energy for nucleation. So we see that the activation energy for nucleation also decreases when the number of special crystallographic orientation relations increases, although the changes are subtle. So there's not very big changes, but yeah, still this point is significantly lower than that point. The activation energy is a few times larger than the thermal energy of the system, as you see here, depicted by the Boltzmann factor times the temperature. So it's maybe good to discuss some of the subtleties of these measurements. The absolute value for the psi parameter that we obtain from the fits is of the order of 10 to the minus 7, joule to the power 3 meter to the power 6. Which lies in the range of values that we reported earlier, as you can see here. And the absolute values of the fitted psi parameter are very sensitive to the value of the delta GS that we assumed and took from the literature. So to illustrate that, if we change the strain energy from 0 to 1.1 times 10 to the 7, which is the driving force at the start of the transformation, this psi value changes from 10 to the minus 4 to 10 to the minus 8. So this is 0, strain, and these two numbers are related. So the trend of decreasing psi value with increasing number of special crystallographic orientation relations, that stays the same in case the strain energy is approximately the same for all the nuclei with the 1 to 4 special orientation relations. And we think that this is the case because we see that the transformation started all approximately at the same temperature. So this start temperature is for 3 and for 2 is all approximately at the same temperature. So that indicates that strain energy is the same in all these experiments for these 4 different nuclei. So we see that there is a spread in orientation relations around Nishiyama-Wasserman and Gurdjieff-Sachs, but Gurdjieff-Sachs has the largest number, and the probability for nucleation increases with the number of special crystallographic orientation relationships between the nucleus and the surrounding matrix grains. Now, what we also could derive from these measurements, which I personally find interesting, is how big is the critical nucleus? Now, it ranges somewhere between 6,000 to 8,000 atoms. It depends a bit on the number of special crystallographic orientation relations. Okay, so now we know that crystallographic orientation relations are very important. We have managed to correlate it to the activation energy for nucleation. We've also seen that strain energies play an important role. But another important factor is the composition of the alloy. And this is the PhD work of Monica Krugler, where she looked into the composition influence on austenite formation from ferrite and cementite in a series of iron, carbon, manganese, silicon steels. So she did quite an amazing job in studying a large number of alloys with different composition, and they can be divided in 2 groups, alloys with 2 weight % manganese, as you see here, and she varied silicon concentration from 0.1 to 1.9, and alloys with a little manganese, 0.1, where also the silicon content was varied, as you can see in more detail here. The thermo-mechanical treatment was casting in a vacuum furnace, rough rolling to 40 millimeters, homogenization for 12 hours in argon, or not, to compare between homogenized and non-homogenized, removing the decarbonized layer, and hot rolling to 4 millimeter, then primary characterization, and then cold rolling to 1 millimeter, and then it was heated at 3 different rates, 0.1, 1, and 5 degrees per second, and we looked at homogenized versus non-homogenized. Well, in this presentation, I will focus only on the slowest heating rate and on the homogenized material and the 2 manganese steels. So when we characterize the starting microstructure, so this is the hot rolled material for the lower content of manganese, and here the higher content of manganese, we see a higher fraction of cementite in the perlite in these alloys than in this case. And we also see here grain boundary cementite. So in the end, we have lower fraction of perlite in these lower manganese containing alloys. And you see that whole analysis here as well. And the volume of perlite is higher in the higher manganese alloys and lower in the lower manganese alloys. But the carbon content in the perlite in the higher manganese is lower than the carbon content in the low manganese. That's around 1 to 1.5% of carbon. What we also see is that in the alloys with 2% of manganese, the silicon, substantial amount of silicon can dissolve in the cementite. And so this is the alloy with 1.9% silicon, and 1.3% can be incorporated in the cementite in case there is also a substantial amount of manganese in it. Here we see there's lower amount of manganese in the cementite, yet the overall alloy has a substantial amount of silicon, but there's only a relatively small amount, but still a amount of silicon in the cementite. And that's, you see here that there's little silicon in these alloys at the places where you have the cementite, here where the carbon is high. After the hot rolling, the material was cold rolled, and then upon heating, the deformed microstructure recrystallizes. So this was the ferrite microstructure, and here you see the cementite before we start forming the austenite. Now in this graph, which is quite a full graph, but I would like to draw your attention to this part of the graph. Here you see temperature, and here you see the silicon concentration. So these are the different alloys with different silicon concentration. And what you see here is that the temperature at which the transformation to austenite started, which is here in green, corresponded very well to the theoretical calculations with thermal calc, assuming para-equilibrium conditions. And if we zoom in this part and where we actually plot the difference between the experimental start temperature and the equilibrium temperature, we see indeed that there's a small overshoot before the transformation starts. So that's as you would expect it. The actual transition temperature is a little bit higher than the theoretical prediction under para-equilibrium conditions. Here it's a little bit below, which could mean that maybe ortho applies better, or it's 10 degrees. It could also fall all within uncertainties. And then the question is, how big is the driving force for austenite nucleation, and what is in fact the composition of the austenite nucleus? Here you see the Gibbs free energy as a function of the carbon concentration. This is the ferrite Gibbs free energy curve. This is the austenite Gibbs free energy curve. And here you see the common tangent between the ferrite and somewhere far away is the cementite. And this is the parallel tangent, parallel to this one. Here you could assume, well, maybe the austenite nucleus takes the composition of the perlite, and then we have this driving force. Or it could be that your austenite nucleus is higher in carbon because we have a larger driving force here than we have over there. So we will assume that the austenite forms with a higher carbon concentration because the driving force is then larger. So then you can calculate what the austenite concentration is, depending on the silicon concentration of the alloy, and for the homogenized material. And these are the points where we have the maximum driving force. And you can see that the carbon concentration can be very high, up to the point where you reach or close to the maximum solubility of carbon in the austenite. So the driving force for the nucleation increases accordingly. So for the higher silicon containing alloys, the driving force for the austenite nucleation is higher here. And yeah, because we know how much carbon there is in the austenite when we assume that the maximum driving force applies, and so that's basically this. If we assume the maximum driving force applies, this is the carbon concentration of the austenite nucleus. We know how much carbon is in the cementite. We know how much carbon is in the ferrite. We can then also calculate, what fraction of the volume of the austenite nucleus is in the cementite and what fraction is in the ferrite, so that the cementite is high in carbon and ferrite is low in carbon, so that the total composition, carbon composition of the austenite nucleus is equal to the one we found here. All right. Now, if you follow what happens as a function of the silicon content, you see that this ratio between alpha and theta decreases, and that's because the carbon content of the nucleus increases. So if the carbon content of the nucleus increases, the nucleus should be positioned further to the left, more into the cementite. So if the cementite gets bigger, this number gets bigger, and the ferrite gets smaller, so this ratio goes down. All right. Then we look at the strain energy and the misfit. And we can look at the misfit between the austenite and the ferrite and the austenite and the cementite. So to calculate the misfit strain, we can apply this formula where here you have the misfit and here you have a geometrical parameter, which if we assume a sphere, we can equate it to 1. And here we have the shear modulus of the matrix. And the misfit is defined as the atomic volume of the precipitate in the matrix. And the precipitate can be the austenite, and the matrix is either the ferrite or the cementite. So then we need to know how the atomic volumes depend on temperature and composition. And these formulas can be found in the literature, where you see temperature dependence and dependence on concentration of manganese and silicon. This is for a ferrite, for austenite, and for cementite. And you see also the dependency on the carbon concentration. And since the carbon concentration here changes also with the alloy, it's important to take the right value here for the carbon concentration in calculating the misfit. So if we do all these calculations, we can compare the driving force for the nucleation to the misfit strain energy. And we know that nucleation is only possible when the driving force is larger than the strain energy. So in this regime, the green line, the driving force is larger than the strain energy. So here we can see austenite nucleation, which we indeed experimentally observed from our dilatometry measurements that the transformation had indeed started. But in this case, the strain energy is larger than the nucleation driving force. So nucleation should not take place. Nevertheless, we did observe it. So if we now assume that the strain energy is the misfit, I should say, with of the austenite nucleus with the matrix is solely accommodated by the ferrite and not by the cementite, then the strain energy would reduce. So that's the calculation here in the black line. So the assumption here is that the soft ferrite accommodates the misfit between the nucleus and the matrix. And there's no accommodation of the misfit in the theta, because the energy penalty for that is higher than for the ferrite. And in that case, nucleation can just happen, and that's also what we experimentally observe. And then we have this last point where there's too little driving force to explain why we still observed austenite nucleation, because all the calculations show that the strain energy is too high to form a nucleus, but we nevertheless see it. Yeah, it could be related because it was also observed that, yeah, the transformation started earlier than predicted under para-equilibrium conditions, or yeah, something else could take place. But for this point, we don't have a full explanation, but in the other points, the model works well, and we can take into account the composition of the alloys in a good way. Now, then we have composition effects related to vanadium carbide precipitation, and this is the PhD work of Gisula Yanadu. And here she studied vanadium carbide formation during the austenite ferrite phase transformation in steel. And here you see the ferrite matrix, and if you zoom in, you see here these beautiful rows of precipitates, and here with the atom probe, you see them as well. And this was the heat treatment that was carried out on 3 different alloys with carbon, manganese, and vanadium. And we performed atom probe tomography measurements. And what you see here after 5 minutes of annealing at a temperature of 650, that the precipitate contains of vanadium and carbon, but a small amount, and there's a fair amount of iron. Whereas after 10 hours, the core of the precipitate has the expected vanadium carbide composition, but the more you go towards the boundary of the precipitate, the lower the vanadium and the carbon, and the higher the iron. And we see the same kind of thing in the SANS measurements, the small angle neutron scattering measurements, where initially the vanadium carbide precipitate turns out to be rich in iron and relatively low in vanadium. But as time goes on, the annealing time at 650, the precipitate enriches in vanadium and decreases in iron content. And this could be measured by comparing the magnetic and the nuclear contrast in SANS measurements. Because if the nucleus contains more iron, the magnetic contrast is different. So if it contains more iron than when there's little iron in it. So this is the way we could detect how the composition of the precipitate evolved as a function of time on the nanometer scale. So we have a core rich in vanadium carbide, but a shell that is more rich in iron. Yeah, and the reason we think that in the beginning the vanadium carbide precipitate is rich in iron, that may be because the iron may reduce the strain energy, and if the strain energy is lower, that will reduce the barrier for the nucleation, as we've seen before. Okay, so the overall conclusion is that detailed mechanisms of solid-state nucleation are not yet fully understood. We made some progress, but there's still more to learn about the system. And the difficulty lies in the interdependencies between the composition, deformation, temperature, and the nucleus characteristics, meaning the shape, strain energy composition, and interface energies, which are all complex, and observations of nucleation at a nanoscale in a fraction of a second, that remains very challenging. And last but not least, abstract submission for the PTM conference is open. So please, if you want to know more about solid-state phase transformations, join us in Delft in July 2025 for this conference. Thank you very much for your attention.